Good afternoon. Welcome to today's Liftoff webinar. We are the National Advanced Materials and Manufacturing Innovation Institute, NetLift. We are advancing American manufacturing through technology, innovation, and talent development with the core mission of ensuring the transition, scale up, and fielding of advanced materials and processes that support our nation's economy and security. As a public-private partnership, we're focused on strengthening the defense industrial base and connecting and convening government, industry, and academia to accelerate the transition of advanced materials, manufacturing processes, and systems engineering. Welcome, everyone. My name is Christine Longroy, Vice President of Business Development here at LIFT, and I'm excited to welcome Dr. Jeremy Eiton, the Chief Technical Officer at Elementum 3D, who will be sharing insights on additive materials reinvented, unlocking new possibilities. It's a critical area of focus as we work together to close the materials gap in the manufacturing sector. As the Chief Technical Officer, he leads the company's materials and technology development at Elementum 3D. He co-invented Reactive Additive Manufacturing, RAM, which you're going to hear about today, and guided development and commercialization of a dozen new alloys for additive manufacturing. We are going to have a question and answer at the end of the presentation today, so please use that Q&A feature on and ask your questions, which we'll get to at the end of the presentation. So Dr. Eiton, thank you for being here with us today, and take it away.
Yeah, thank you, Christine. Thank you, LIFT, and thank you everyone for attending. So quick couple slides about Elementum 3D. Our core business is the high performance AM metal feedstock powder development and supply. As part of that, we are doing AM material process and application development and qualification. So we help everything through to theoretically developing the feedstocks, experimentally developing them, producing and supplying them to industry, supplying process parameters, process development, material property data sets, in some cases all the way towards MMPDS, S basis or CD, CD basis data sets that we're putting together, and then helping parts with application development and qualification. One example of us, that we're pretty proud about succeeding in this new development and supply is we did win the U.S. Air Force Rapid Sustainment Office's Advanced Manufacturing Olympics gold medal in the materials category for our 7050 RAM2 based aluminum alloy. We are also one of the co-exclusive license holders for GRX 810. That's a NASA developed oxide dispersion strengthened alloy. So we supply that. And we also did a lot of the early work with NASA on GR COP 42 for large format printing process development. So we're really looking to create new materials to power the next frontier. We've been able to work with NASA, and including Marshall, JPL, Glenn, and others. But with JPL, they actually last year launched the very first part that was fully qualified to the NASA 6030 standards. And that part was produced out of our 6061 RAM2 alloy. We're involved in Formula One racing. We have our materials in the engines of Formula One race cars helping win races. We're involved in energy and aerospace, and also defense and propulsion, and other areas as well. Our facilities are located in Erie, Colorado. That's just north of Denver, just east of Boulder, Colorado, and kind of between the airport and Boulder. We have two facilities, both about 10,000 square feet. They're within 2 miles of each other. We have printers in those facilities, EOS M290s, M400s, SLM 280s. We also own an SLM NXG 12 laser system that is currently in Lübeck, Germany at SLM, but we're looking to bring that over very soon. We have advanced aluminum atomization capability that's in development coming soon. We have RAM powder production capability. We have over 27 technology patents, about 40 employees. We work with over 220 customers in additive manufacturing or users of additive manufacturing products. About a 400-ton annual production capacity for powder currently. We are ISO 9001 and AS 9100 certified. We work within the DFARS NIST 800-171 type environment related to CMMC, ITAR registered. We also have a federal firearms license. And we have an in-house metallurgical lab where we can do metallographic analysis, optical and SEM microscopy. We have an Exum mass box, mass spec that we can do chemical analysis with, an Anton PAR laser diffraction system for particle size and other equipment. So materials technology, really is critical for the technology of a civilization. If you look at archaeological eras, they're typically named after the materials technology available at the time: Stone Age, the Bronze Age, the Iron Age, and so on. And today, many people kind of have referred to this as the aluminum age because of the recent prevalence of aluminum being used, very widely for the first time in the last 100 or so years. But also the silicon age because of the computational explosion that we've had. And also it's been called the age of composites because of the real prevalence of engineered composites. Composites, of course, in general have been used for centuries. Concrete is an example of a composite, and wood even is a composite. Now, a quote that Tony Bromwell at Lyft gave recently that I really liked was that about 70% of technology innovations are dependent on the materials innovations. So it really stresses the importance of new, better materials enable new, better technology. So with materials, processing, composition, structure, and performance are critical. Material processing and composition determines the structure and the performance. And printing a legacy alloy composition may not result in the same structure or properties that you obtained with the traditional processing. So new designed for additive manufacturing materials are really needed today. Looking at laser powder bed fusion of aluminum alloys, there's a big problem with hot tearing. This is a solidification cracking that happens because of the microstructural growth that happens during solidification. You get very columnar and dendritic microstructure that forms, and in between those columns, you have inadequate backfill of the liquid phase that leads to cracking between those very large columns. You can see that part on the left. The columns are visible on a macroscopic scale. They're millimeter type scale columnar growth that takes place with cracking between those. This is very common where you take an alloy that was designed for wrought processing, like most high strength wrought aluminum alloys, for example. If you just try and take that same composition and print it with a powder bed fusion process or other fusion process, you tend to get this type of microstructure, and you have problems with cracking, and it's functionally unusable. In this example, this is a printed 2024 aluminum alloy. And because of this, you would get very brittle fracture at low strength, essentially unusable. You might be able to make something that looks like a part, but just don't apply any stress to it. So what you need is microstructural control in additive manufacturing to get the properties that you want. Just taking a legacy alloy, printing it doesn't always work. You can control the properties that you get by controlling the columnar to equiax transition during solidification. There's a few ways to go about this. So one of those is you can optimize the alloy that you're working with. You can make small changes to the alloy that can help with changing the transition from columnar to equiax. However, if you're working within a specific alloy system, you only have so much flexibility before you've completely changed your material. And that limited flexibility can make limited changes to your transition from columnar to aqueous solidification. You can also change your process parameters. If you change your laser parameters, your power inputs, your travel speeds, things like that, you can control your solidification microstructure within a certain extent. However, those process parameter changes also do affect your production speed, so you can slow down your production, which isn't very desirable if you're messing with those too much. But also within a given process like laser powder bed fusion, you are sort of limited to a window that works well, and you can't completely change your solidification structure generally within that window that works well. So there's another method, and that is introducing heterogeneous nucleation sites, and that's what I'm going to focus on talking the most about here. So in solidification, you have homogeneous solidification, and you also have heterogeneous solidification that can take place, or heterogeneous nucleation that can take place. And heterogeneous nucleation is where you're solidifying your bulk material onto a secondary structure. It could be the side of a container wall if you're doing a casting. You can initiate your solidification from the container wall. But if you can provide a dispersion of very small seeds within your liquid melt pool, you can also solidify off of those seeds. And that can help you to get a very fine aqueous microstructure. The math behind this is essentially that you're reducing the barrier of nucleation. When you are forming a nucleation crystal, you have surface area interaction energy that is kind of unfavorable. You don't want a lot of surface area interactions, but your volume energy change when you're below the solidification temperature, below the melting temperature of the material, that's favorable. So you have a minimum size of a stable nucleus that you need. If you're below that size, your surface area is too high and it's unfavorable. If you're above that, then the volume energy dominates and it's favorable. So this is some of the things that you need to consider when you're looking at the right nucleation sites to introduce, how you go about that, and what sizes will work and what won't work. In general, you want these to be good inoculants or crystalline, thermodynamically stable above the solidification temperature of the bulk alloy. You want high lattice matching with primary alloy crystal phase. So having lattice matching will help with allowing the primary phase to solidify off of those initial inoculants. You want chemical affinity with the bulk alloy. It needs to wet, it needs to have some affinity. And you want numerous and well dispersed without producing deleterious effects from having the wrong elements in your alloy. So the approach that we are using extensively at Elementum 3D and that we've patented is we've termed reactive additive manufacturing, also known as RAM. And so this is inspired by reaction synthesis. Reaction synthesis is forming product phases from in situ reactions that are energetically favorable from reactant phases. This enables the use of traditional AM micron scale reactant powders while forming submicron or nanoscale product phases in the solid parts. So we don't have to work, ideally you want your inoculants to be nanoscale, but working with nano-sized powders isn't always very friendly. Many materials at the nano size will rapidly pick up moisture or oxygen from the environment, for example. They can potentially get airborne, things like that. So we do not work with nano powders for these RAM materials. We're able to work with traditional micron scale feedstocks. This also allows you to use reactant species with lower melting temperatures than the product species to promote full density parts. If you try and just put in high melting temperature ceramic phases into your feedstock powders, you may have trouble with fully melting those, getting bonding and wetting between the alloy system. So that can be very challenging. Also, the very high surface areas can lead to gas inclusions and so on. So we were working with reactants that can then melt and dissolve into the alloy systems and then precipitate out very high temperature nano phase precipitates to provide the dispersion strengthening and inoculation. Particulates also improve the strength, the elevated temperature performance, wear resistance, and can reduce the coefficient of thermal expansion of those alloys. So you can use the type and the amount of those product phases that you're forming to control your properties, leading to tailorable properties. Not only does it make many alloys that otherwise would be unprintable printable, but it allows you to improve and tailor the properties towards your applications. This is one of the few ways, for example, that you can really improve your modulus of your materials. Modulus, your stiffness, is something that's very hard to do within a given alloy without completely changing your alloy. But adding in, making a composite type material with ceramic particulates can have a significant effect on your modulus. You can significantly stiffen your material with relatively small compositional changes. Here's an example looking at a 6061 based aluminum alloy. So on the left is the standard wrought 6061 composition. If you try and print that with laser powder bed fusion, you can see in this EBSD image the columnar type structure looking at with the growth direction going upwards. So each layer the solidifies on the previous layer below on those same crystals, and then builds those crystals upward until they're millimeter scale macroscopic crystals, and leads to cracking between those. The colors that you see there are also very similar, which shows that those crystals tend to be oriented in similar orientations, which is also not great for having properties that are equal in all directions, and also tends to lead to more problems with the cracking. So if you look, as you start adding these RAM reactive inoculants into the system, a RAM 1, for example, is a nominal 1 volume % of product phase, reactive product phase that's formed during the printing process. And you can see that's now a completely different microstructure. You can see the scale bar is also different than the legacy alloy because we're now looking much closer because the grains are so much smaller already at nominal 1 volume % product phase. At this point, we've completely eliminated any solidification cracking problems, drastically improved the properties. And a RAM 2, we've standardized many of our products around a RAM 2 because it provides a fully refined microstructure. You can see under 2 microns average cross-sectional grain diameter, and good isotropic properties. You can also move to higher RAM contents like a RAM 10. For RAM 10, you don't get a lot of further refinement. You're already pretty much fully refined by a RAM 2. However, you do get increased properties based on the composite that you're forming. So you get the benefits of both the ceramic phases that you're forming as well as the metallic phases. So you can increase your stiffness, your strength, your high temperature properties, and so on. So this is where you could also do a RAM 5 or a different RAM content to really target the exact combination of stiffness, strength, high temperature performance, ductility, and so on that you're looking for. So what is this reaction synthesis that reactive additive manufacturing is based on? Well, reaction synthesis is broad and includes self-propagating high temperature synthesis, or SHS. I've done a lot of work in this area, but it also includes non-propagating reactions. It includes things like thermite reactions, includes gas phase reactions. So it's very broad. It's basically synthesizing materials through a reactive process. It also includes a range of different reactant product systems, including metal matrix composites, ceramic matrix composites, intermetallic composites, and functionally graded materials that can be formed. It can also be used for joining, welding, cladding, and also together with traditional forming processes, so in combined processes. I have a video here that's an example of a self-propagating reaction of a pressed powder pellet. So we took powder metals in the right composition, pressed them together, and then ignited it from the top. And you can see now, this is the ignition, and now the reaction has started. And in this case, it's a self-propagating reaction. The reaction releases energy that is sufficient to ignite the adjacent material, and it propagates in a wave-like fashion, very controlled in a downward fashion. So the thermodynamics behind this, I'll touch on in a little bit, but you can control this process very precisely. You can make it so it propagates in a controlled way. But in the case of reactive additive manufacturing, we're actually controlling it so that it does not propagate. Where the reaction only takes place, like in a laser powder bed fusion process, it'll only take place where the laser is actively melting the material, and it won't propagate outside of that area. So self-propagating high temperature synthesis thermodynamics are based on enthalpy terms. So you've got the reaction enthalpy, you've got the heat capacity of the product material and the reactant material, and you've got the phase change term. So if you're melting the material, if you're changing your crystal structure, there's enthalpy associated with those. And if you do an enthalpy balance, you can now calculate your adiabatic combustion temperature. So the energy released through heat capacity will produce a temperature in your product material, and that's the energy and temperature gain you gain from the reaction. So in reactive additive manufacturing, although it's not a propagating process, you still do get some temperature benefit from the reaction. So these favorable reactions will help with reducing the laser energy input you need, and help with distributing that energy. So instead of just the laser energy on the surface of the material, you can get a broader distribution of energy through the reaction to make for a more favorable processing of the material. So it can help a little bit with production speed of your material, can help with controlling your melt pool dynamics, can help with making sure that you achieve a fully dense product phase in a very favorable production speed. So you can print faster, more economical, and achieve higher densities and better products in the end, basically. So if you had a thermocouple on that pellet that I showed reacting just a minute ago, this is kind of what you'd see. Initially, you would be at the starting temperature, and then you'd have a very rapid spike when the reaction wave is passing or taking place in your temperatures until you achieve your combustion temperature, and then you'd have a slower cooling process. And again, this is the propagating type mode in a laser powder bed fusion. All of this is taking place much more rapidly and only locally within the melt pool on about 100 micron scale. Some example reaction systems that can be used with reactive additive manufacturing include all of these: titanium carbides, titanium diborides, silicon carbides, tungsten carbides, and so on. You can get into much more complicated reaction systems, nickel titaniums, moly disilicides, but also oxide and carbide or oxide and boride composites, things like that. And you can predict the energies of these reactions, as well as the combustion temperatures, the heat and the temperature that you'll get from the reactions. Now, to control the reactions, this is where you can add in diluent phases. You can either add in pre-synthesized product phase, or you can add in metals. In our case, we're typically adding in metal alloys that you want to produce, in addition with these smaller amounts of reactively produced ceramic type products like carbides and borides. And so by controlling that balance, you can control the energy from the reaction versus the energy, the input needed from the laser. And you can control the composition, particle sizes that you're forming, phases that you're forming, and so on. You can also do gas phase reactants by controlling your process gas, for example, using nitrogen instead of argon, adding in controlled amounts of oxygen, things like that. And you can therefore form oxides, nitrides, hydrides, or other product phases using gas as well as solid phase. Mostly what we're doing is primarily solid type reactions. However, we have looked at gas phase reactions as well. Here's another example of a ROT 5083 composition, designed for ROT processing that's been printed with laser powder bed fusion. And you can see in this optical micrograph the very large columnar and cracking microstructure that's developed here. There's extensive solidification cracking along those columnar grain boundaries. Here's RAM versions of this material. There's a RAM 2, so a nominal 2 volume percent of product RAM constituents, and a 5 volume percent. And you can see now that scale bar there, if you have any trouble seeing, is 15 microns. And so the average grain size that you're looking at, cross-sectional grain diameter, is on the order of 1 to 2 microns for these materials. And you can see the nanoscale or larger, nano to micron scale product phases that are also forming. In this case, the brighter contrasted areas are largely the product phases. And you can see that there's a distribution of both micron scale, but also nanoscale product phases. So what do the properties look like for these alloys, and how do they compare to the wrought traditionally produced materials? So these are printed values from the as-built condition. In this case, 5083 is known as the highest strength commonly used aluminum alloy that does not require heat treatment to achieve the strengths. And so these green bars are our RAM 2 and RAM 5 printed materials, and they're compared in this case against the legacy wrought produced 5083 alloy in a work hardened and slightly stress relieved condition, but primarily benefiting from work hardening. And so in the printed materials, you can see even without the true work hardening, there's some internal stress from the print process, but you can see the strengths are much higher. And actually, if you do a stress relieve on these printed materials, it maintains essentially identical strength. You don't see a strength drop in this material, even with the stress relief, which you would typically see from other printed materials. So the strengths from both the RAM 2 and the RAM 5 are much higher than the legacy wrought product, even though the wrought product is in a strain hardened condition. Elongation of the RAM 2 is essentially equal to the traditionally produced wrought product. The RAM 5 does have a little bit of decreased elongation, but still a 9 or 10% elongation is still a healthy elongation for an aluminum alloy, with the strengths being a good 50% higher or so than the strain hardened wrought produced product. So looking at RAM aluminum composites a little bit further, you can see that they also benefit greatly from, in wear resistance. On the left is one of our aluminum metal matrix composites. In this case, it's a RAM 10 2024 based aluminum alloy. And the bar chart there is the amount of material that's lost due to wear in the equivalent test for each of those three materials. So the aluminum alloy bar being the smallest means that it lost the lowest amount of material, which is good. The 17.4 precipitation hardened stainless steel, you can see lost over 3 times the volume in the equivalent test. And an A380 cast aluminum alloy is also shown there for comparison, also showing much higher wear than the composite material. So basically the ceramic composite, ceramic phases being very hard and wear resistant can help make wear resistant composites that are also ductile, high strength, high performance overall. I mentioned a little bit that you can control specific stiffness or modulus with this process as well. Here's an example of our Elementum 3D 1000 series aluminum RAM 15 composite. And it's shown compared to a bunch of elemental metals: magnesium, aluminum, titanium, zinc, copper, iron, nickel. And if you followed that line upwards, you would see others, molybdenum, tungsten, and so on, also fall either on or below that line. Almost all elemental metals fall on or below that line for modulus versus density. There are a couple exceptions, beryllium being the most notable. But if you really want to get above that line, you have to start moving into ceramics or composites. And so this is where Supreme X is a Materion produced alloy designed for high specific stiffness, made for traditional manufacturing, not printable. But you can see our printable material now is comparing quite well to the Supremex traditional high specific stiffness composite material in a printable form. So this RAM process, it's versatile. It's applicable to many different alloy systems, not just aluminums. Here's an example in nickel superalloys. This is looking at an alloy 230, like a Haynes alloy 230 type system, which is known to be weldable by traditional processing. But when you get to the very high thermal gradients of laser powder bed fusion additive manufacturing, you do get these micro cracks throughout the alloy that form. So you get very small cracking along the grain boundaries from solidification-based cracking and a very columnar microstructure that forms. So how do you solve these? Well, the RAM process is also suitable for solving this. You can see the EBSD colored image at the top of those microstructures. We've moved from that very highly textured oriented microstructure to a more randomly distributed, more equiaxed microstructure, and that's completely eliminated the micro cracking that would otherwise be present. This also helps greatly with the properties that you're forming. You can see in that chart there, those are looking at the total elongation versus yield strength of different alloy systems. And you can see the blue, that's the wrought alloy, so good elongation. But the yield strength isn't nearly as favorable as those gray dots on the right. The laser powder bed fusion traditional alloy and printed, because of those micro cracks, you get poor elongation. The strength is actually relatively good because of the additive manufacturing process. However, the elongation is nowhere near what the rod is. But the gray is looking at our development that we did, funded by the Office of Naval Research, together with the Colorado School of Mines. And we looked at a wide range of different RAM type and inoculated type compositions. And so those dots, the scatter you see is because those are all representing different compositions, different process parameters, and so on. But if you look at the preferred compositions in the top in that green circled area, those are the type of performance you expect now with the most favorable preferred composition that we've selected for our product. And so you can see the elongation is comparable to the wrought, traditionally produced wrought plate, but the strength is actually significantly higher. And you can also see, even if you look at creep, the creep performance is also much improved compared to the unmodified alloy in the printed form. Those are showing the creep performances at different stresses, and you're getting much longer creep life as well as less creep strain for a given amount of time and stress. So a little bit of insight into this behavior from model prediction. So we've worked with Colorado School of Mines, Dr. Yona Klemtool especially, on development of these models for understanding and explaining solidification cracking, the columnar to equiax transition in different alloy systems. Haynes 230 was a big one that, because it was traditionally weldable, it wasn't well understood. Well, why isn't this more printable? It's not a gamma prime strengthened nickel superalloy, but we were able to explain here why that alloy had struggled in laser powder bed fusion type processing conditions with micro cracking. So looking at the process with laser powder bed fusion in that blue line, you can see that on the right side, you're forming equiaxed solidification. On the right side, you're forming a columnar solidification. On the left side, you're forming equiaxed solidification. And so what you want to do is you want to have your columnar to equiax transition, those colored lines, the red, yellow, and green lines, for example, or black in one case, you want those lines to be as far right as possible so that you're forming primarily equiaxed solidification rather than the columnar solidification. So the base Haynes 230, we calculated this, and we found that it's way over there with that dashed type line, and therefore you're primarily columnar solidification in laser powder bed fusion type processing conditions. We looked at a bunch of different compositions, including alloying additions as well, or alloying modifications, as well as adding inoculation sites. And you can see that in the green areas, we found that there was no solidification cracking with inoculation site additions through the RAM processing. And those now you can see in some of the cases, you're actually even getting into further to the right, the columnar equiax transition, even than like an Inconel 718, which is a known, friendly to print alloy. So what we really need for additive manufacturing, we need consistent and easy to use AM feedstocks with high performance. Here's some examples. In this case, printing 17.4 precipitation hardened stainless steel. And you can see the problems with internal stress causing those parts to delaminate from the plate. The internal stress causes the parts to kind of smile right off the plate and come loose, curve. You can get part distortions. You're not producing the geometries you want to produce. You're losing contact with the plate, which can lead to complete build failures. And so this is a big problem. You don't want to have PhD researchers to simulate and try and make a build work. You want it to just be easy to use, have a technician that can produce a build that works on their first try. That's the goal. That's what we really need in this industry. And so part of that, we were able to modify this alloy to make it printable, highly printable, highly repeatable, as well as modify the design to optimize and take advantage of AM capabilities to maintain the strength where you needed it and not spend extra time and cost printing parts where you don't, printing material where you don't need it. So here's an example using 316L stainless steel with our modified 316 microstructure. So on the left is the standard 316L microstructure. You can see average cross-sectional grain diameter about 27.5 microns. Now our modified composition, we've cut that grain size at about approximately in half and made it more isotropic. Looking at material properties, the goal of this project here really was to get isotropic, consistent, reliable properties in an easy to print type material. So it wasn't to make it as high strength as possible in this case, but just make it easy to print. And you can see that the optimized RAM-based material compared to the wrought material, we're achieving better strengths than wrought material, better properties than the wrought material. But compared to printed base alloy, we're also achieving much more consistent properties in the X, Y versus Z orientation. So on the right there, that's the difference between the X, Y, and Z orientation. And so the higher those bars are, the less the difference between the X, Y, and Z orientation. So the RAM material is much more consistent in all directions compared to the base 316L material. So here's a little bit of mention of NASA invented GRX 810. So we've commercialized this material based on NASA's development. We've scaled this up to commercial production rates. From NASA was initially producing kind of a kilogram an hour through 2 systems. We've been able to scale this up so now we can produce ton type quantities, ton scale lots for commercial producers and customers, and we're supplying this today. This alloy is exceptional for extreme environments. Creep performance is amazing compared to other like nickel superalloys, for example. And you can see that compared to some of these other materials, looking at other materials that are relatively good in creep, Inconel 625, Haynes 230, Haynes 233, 188, Inconel 617, Haskell X, and even a nickel cobalt chrome oxide dispersion strengthened alloy there in the dark blackish colored dots and dash line. Now the GRX 810 in the yellow on the top, that's showing that the creep performance really is exceptional compared to these other options. This GRX-810 is a nickel cobalt chrome based alloy, but there's other alloy in additions to that. And then there's also a nano yttria oxide dispersion within that alloy. So this leads to about 2,000 times creep life compared to AM nickel cobalt chrome alloy. The oxidation resistance is also greatly improved. So you can use this now at temperatures where you wouldn't traditionally use most nickel superalloys, like 1100 degrees Celsius and above, for example. You're still limited, of course, by the melting temperature of the alloy. But you can now use this in temperatures where historically you would not put a nickel superalloy due to both the creep and oxidation type concerns, as well as rapid strength degradation in those other alloys. On the right there is the creep rupture life shown compared to some of these other alloys, including oxide dispersion strengthened rhenium boride, nickel cobalt chrome oxide dispersion strengthened alloys, and base nickel cobalt chrome alloy. And you can see all of those are bunched into those vertical lines on the very left of the graph. None of them are even on the same orders of magnitude as the GRX-810 alloy. So this is another example of a different approach for dispersion strengthening. So I mentioned the RAM dispersion strengthening approach. This approach is actually using pre-synthesized yttria that's coated onto the surface on a nanoscale onto the other materials. So because it is coated onto the bulk materials, nanoscale materials, you don't have some of those other concerns that you might have with a free nano type powder because it's now a coated micron scale product. So what about printing of larger structures? I talked a lot about laser powder bed fusion, but these powders can also be used, and we are using them for laser powder DED processes as well. On the very right, there's an image of me holding an aluminum RAM produced laser DED component that we did in a collaboration with NASA. And then we're also making wire form versions of these materials with Fortius metals that has an exclusive license for wire form based RAM materials. And so they're making wire for wire DED processing, but it could also be for traditional welding of high strength materials that would otherwise be considered unweldable because of the RAM inoculation capability that it brings. So to expand a little further on our family of materials that we have a family of aluminum alloys many of them based on wrought alloy products that otherwise would be unprintable, but also based on composite type products and high strength custom alloys that otherwise would not be producible by additive manufacturing. We have a family of nickel alloys, including a nickel alloy 230 RAM product, Inconel 625 RAM product for improved performance. With the 625, you can get performance comparable to a 718 type material without the need for the complex heat treatment that 718 would require. GRX-810, as I mentioned. We've also worked with other more, customized nickel alloys like Inbar 36, for example. We have copper alloys that we've been working with. We have a commercially pure high conductivity copper. We have a copper RAM alloy that we're developing that we plan to release here in the not too distant future with a couple versions of that. One for very high conductivity with excellent printability. Copper is challenging to print to full density because of the reflectivity of the material as well as high conductivity. But this RAM alloy can solve some of those problems, make for a very printable high conductivity material. And then also, we've done a lot of work with GR-COP 42 together with NASA in commercial space and other customers. Cupro nickel together with the Navy and other commercial customers. And then we have a high operating temperature copper RAM product as well that maintains the properties and performance at high operating temperatures with the good printability. We've worked a lot with refractory metals, tungsten, tantalum, rhenium, molybdenum, and alloys thereof, and also with steels. So thank you very much, everyone, for attending. And now I'm ready to, take any questions.
Thanks, Jeremy. Great presentation. Lots of detail. Obviously, materials is the power to the next frontier, for sure. So thanks for sharing that. And as you started out, it really is the power of lift and what we're intended to do as a Manufacturing Innovation Institute. You mentioned Exum, and you're using that technology. You talked about Tony's presentation and what he said, our own Tony Bromwell, about materials. So this really is the power of lift. So I encourage anybody that's not a member of lift that's attending this, please consider to joining us. So we do have a couple questions that have come in our few minutes that we have together. Are any of the RAM-based materials easily recycled?
Yes. So there's two things. One, they're very reusable. You can reuse the material many times through the processing. So as you're printing your parts, any material that's not directly consolidated in that part, you can reuse that material. And we've done reuse studies where we can reuse the material dozens or more times. I think one of the studies was up to 60 times, and there was no limit there. That was just the number of times that we tested. So it's reusable and then recyclable as well. You do, of course, have to consider what you're recycling into, which materials you're working with, but most of them are recyclable. Aluminum powders in general are a little bit tough to recycle, aluminum AM powders, because of the oxide shell on those powders, but they certainly can be reprocessed and recycled as well. But primarily reuse is the preferred method, and you can essentially reuse them until they're used up in your parts. So you don't need to, generally you don't need to dispose of the material. You just continue to use it. You can top it up with fresh material so you always have enough to do your builds.
Thank you. Another question that came in, what are the specific challenges that are faced by reactive alloys like titanium, which is the backbone of aerospace manufacturing?
Yeah, so reactive materials, they have a few challenges. The first one is making sure that you're working with them safely. Reactive metals, if you work with them in the wrong way, they could catch fire. They're very reactive, especially with oxygen. Now, with AM-based powders, you're working with micron scale particles. They're generally very spherical, so relatively low surface area for the volume of the particles. And so that helps. And so therefore you can work with these in air. You can work with them safely in the right way. So safety is the first aspect. When you're processing them in your printer, you want to work with an inert atmosphere in the printer. Most of these printers are designed for that type of thing. Our materials are generally printer agnostic, so they can work with all the commercial printers, off-the-shelf printers. There's no need for anything different on the printer side. But most of the time you want to work probably with an argon type atmosphere for reactive metals, especially titanium. You wouldn't want oxygen or nitrogen even present in those atmospheres. A final consideration is that for things like titanium, less so for aluminum, but for titanium especially, you do need to control your oxygen level in that alloy. So exposure to moisture, exposure to oxygen over time can increase the oxygen level, and eventually you may get out of spec oxygen-wise for a titanium alloy. The oxygen will actually increase your strength, but it will also decrease your ductility, so you need to control your oxygen level. So that's something to consider with a reactive metal like titanium.
Thank you for that. I think we've got time for a couple more. What barriers do we need to overcome for RAM to scale broadly? And maybe it's webinars like this and it's informing the industry. So talk to us a little about what barriers we need to overcome.
Yeah, so I think, the powder production side, I think we can do that already. We can produce hundreds of tons of RAM material, so the production is there. But what we really need is I think what we need for additive manufacturing in general. We need to start moving more applications in additive manufacturing from qualification, from prototyping into true serial production, high volume production in additive manufacturing. And that's what we need in general, and that's true also for scaling these RAM materials. And so to achieve that though, we need very good statistical data sets. So that's why we're working on MMPDS equivalent and soon hopefully to be published in the MMPDS data sets for some of our materials. So having those data sets allows engineers now to design in those materials for aerospace applications. And then we still do need to qualify those parts as well. So qualifying those parts for critical applications through aerospace. And then there may be parts as well that maybe don't need to be qualified because they aren't critical for aerospace type applications. And so looking for the right opportunities for easier, lower barrier to entry applications where it makes sense to take advantage of the capabilities of additive manufacturing. There's oftentimes cheaper ways to produce bulk metal. If you want to produce a big block of metal, you're probably not going to print it unless it's a material that requires additive manufacturing. But if you just want a block of steel, you probably don't want to print that steel. So you need applications where it's really taking advantages of what additive manufacturing can do. Things like where you have conformal cooling channels throughout. So like tooling, dies, where you might want to cool and heat those to improve your production speed. So looking for the right applications. And then with the RAM material specifically, I think where you want to push the barriers of what's possible with the materials. So high operating temperatures, having improved strengths, improved stiffnesses, looking for applications where you really need the best performance from the materials perspective, as well as the complexities that additive manufacturing can bring.
Great explanation. And I think this sort of leads into probably what's going to be our final question. And it kind of ties together. Can RAM scale to underwater usage as well? I know you said oxygen is tricky with some of these metals, but can this potentially make its way into the naval submarine space?
Certainly, RAM materials, printed materials, are very stable. They're very good for use in seawater, other areas. And so from the printed perspective, yes, no problem. And from the printing, the feedstock printing perspective, in general, they are usable anywhere that traditional metal feedstocks are usable. So could you have a printer on a submarine? Yes. Could you have printed parts on a submarine? 100%, yes, certainly. Could you do underwater welding applications where you're actually, doing a process underwater, like underwater welding? And that also is yes. You could have RAM-based wires that are used underwater in an underwater welding type process. I don't think you'd want to do laser powder bed fusion underwater, not in a wet environment. So probably laser powder bed fusion you wouldn't do in the open ocean, obviously, but on a submarine, something like that, 100%.
Excellent. So we do have one more question. How complete is the SHS reaction in RAM? And are there contamination considerations for oxide formation or some other inoculant that can be introduced?
Yeah, so, again, the RAM process, we're not using what I would call an SHS, or self-propagating high temperature synthesis. So I'll differentiate a little bit there. With SHS, it depends on the purity of your feedstock materials, your powders that you're using, as well as the atmosphere that you're processing in. So oftentimes you'd want to do that in an inert atmosphere unless you intentionally wanted oxygen or nitrogen to be present. So you might do that in a sealed vessel. Now with reactive additive manufacturing, so that's a non-propagating type process. The reaction only takes place within that 100 micron or so scale of where the laser is introducing the melt pool. And in that process, likewise, just like with any printed metal, you do also want to control your atmosphere. Many RAM materials could be used in nitrogen, could be used in argon. We typically use argon for everything. We have it readily available. We just stick with nitrogen or argon for the most part. There are some systems where we've done gas phase reactions with nitrogen or with controlled amounts of oxygen. But generally, you control your product materials through the purity of your feedstocks, which we control very precisely for our RAM-based products, and then also through your atmospheres in your printers. And the RAM constituents, the RAM-based materials, are comparable in the atmospheric concerns to any of the other printable alloys. So you still want to operate within inert type environments in the printers, just like you would with any other laser powder bed fusion based metal.
Excellent. Thank you for that. That's going to wrap up the Q&A part of it. Dr. Aiken, thank you so much for an insightful, engaging, and informative presentation. Obviously, this work underscores the importance of the need of accelerating of advanced materials, wear resistance, the thermal stability, and closing that material gap, which we care very much about. So thank you for that, and thank everyone for joining us today. Mark your calendars for our next liftoff webinar, which is from Exum Instruments, who Jeremy mentioned in here, another lift member, November 12th, who is going to be presenting chemistry at the point of need. To learn more about Lift, joining as a member, check us out at lift.technology. Thanks, everybody. Have a great rest of the day and week. Bye, everybody.
Thank you.